All right, hey guys, how you doing? I am in chapter 7 now. This is all the way almost towards the very end of the packet, so it's actually page 9 out of 10. Flip all the way to the back, we've got this problem about young women's heights, and I want to compare and contrast some stuff about normal distributions that you guys should remember from chapter 2. Normal distributions where we do like z-scores and draw the graph and shade like the bell curve either left or right when you're given a mean and a standard deviation. So this chapter is really similar to that when we do our mathematics like types of calculations, but a couple different scenarios here. So just to draw your attention to the difference in this very first problem, so part A versus part B, the probability that A randomly selected young woman, that's just a chapter 2 problem. That what is the chances that I grab one woman who is taller than 66.5, whatever. That's when you just do the normal CDF in the calculator, draw the sketch, blah, blah, blah. The difference between that chapter and this chapter is that now that we are taking an SRS of 10 young women, and I want to know what the chances are that their mean height of all 10 of them exceeds that number. That's the new thing. This chapter we're taking samples from populations, and last chapter we just took one specific person, or not last chapter, chapter 2, one specific person and did our normal CDF stuff. So that's the difference, so just be watching out for that because I'm going to be flipping back and forth as we're going through this problem. So let's first remember the state plan do conclude, so I have to first define what the x is that I'm going to be solving for, convert to a z-score, blah, 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 do all the review stuff. So I encourage you to pause the video, see if you can work out letter A, knowing what you remember from chapter 2, and then just check your answer with mine. All right, how did you do? Here's our answer for this one, 0.2119. So just to refresh your memory and to breeze through this really quickly, define what the x is because you're trying to find the probability that x is bigger than this number, taller than 66.5. Remember to state this part too, since the x is approximately normal, the distribution of x, remember, that's what we're given up here. Otherwise, we wouldn't be able to use this z-score calculation to get this percentage if we didn't know that this was a normal distribution. So remember that that part is something that we usually just like skim over and we're like, okay, height of young woman, blah, blah, blah. That is very important to tell us that we can use this calculation. So x is approximately normal. That's what this notation means. And here's the mean and here's the standard deviation. Therefore, I can find the probability that x is greater than 66.5. Check your notation here, because remember they're always really picky with the p's and the z's and what the proportion actually is at the end. There's a almost 21% chance that a randomly selected woman is taller than 66.5 inches. So the next part is find the probability that the mean height of 10 young women. So here's where this chapter comes into play. So we have a couple conditions we have to check. And I just wrote, just to make sure and emphasize the difference here, a randomly selected young woman is not a sample, just one woman. That's a review problem. Here we are taking an actual sample. We have sampled 10 young women, therefore I need to check my conditions. Here's what that looks like. So here is what the condition checks look like. So you're probably like, whoa, that looks like a lot of writing. Yeah, it's a little bit small. I'm going to zoom in here. So remember, two things we need to look for. First of all, that 10% condition, there are more than 10 times our sample size here is 10, which is 100 young women in the population. There's way more than 100 young women in the population. So that means that the 10% condition is met. And remember, once that 10% condition is met, that gives you your permission to change your standard deviation. So your standard deviation of just the sampling distribution is going to be 0.7906 because here's the formula, sigma over radical n. And so what that means is our sampling distribution of x bar is approximately normal with the same exact mean, but a different standard deviation. Remember, when you take a sample, your spread gets less spread out, it gets smaller. So I want you to compare that to the standard deviation we used earlier. Remember, it was 2.5 for just one woman. When we take 10 women, our standard deviation gets much smaller. And then remember for the condition check number 2, since the population distribution is approximately normal, that was given in the problem, that makes this the easiest type of condition check. That automatically defaults to the sampling distribution also being approximately normal. Remember that the CLT would not apply here because n equals 10 and n has to be bigger than or equal to 30 in order to use that CLT. So if you were wondering about that, make sure you get that straight. But this is the easiest situation. Population distribution approximately normal, that means our sampling distribution will also be approximately normal. So now what I'm going to do is the exact same math that I did in the first question, this part A. I'm going to do almost the identical work here for all of this, except the only thing that's going to change is my standard deviation because this is a sampling distribution now, so I'm going to replace the 2.5 with this 0.7906. It's going to give me a different probability in the end result. And here finally is what that math looks like. So notice I made another change here. I'm trying to find the probability that the mean of the 10 young women, so I put an X bar there, so make sure you catch that. It's different from the X that we have up here because that was just one person. Here's the mean is greater than 66.5. Almost same exact calculation, except I'm using this standard deviation here instead of the individual standard deviation. That gives us less than 1% chance. So my interpretation there, just make sure you got that. That means there's less than a 1% chance of that a sample of 10 young women have a mean height greater than 66.5 inches. Okay, next question, ironically enough, is about pregnant women. Actually, it says human pregnancies, not to be confused with like elephant pregnancies or dog or cat pregnancies. From conception to birth varies. Did you know, actually fun fact, that the distribution of length of human pregnancies is approximately normal? Mean 266 days, glorious days of just having a lot of fun and a lot of wonderful things happening to the woman's body, and a standard deviation of 16 days. So again, we've got a review problem and a new problem. So we have a randomly chosen pregnant woman. That's the review part. Then we're taking a sample of 6 pregnant women. That's the new part. So go ahead and do number 1, pause the video, and make sure you check your answer with mine. Here's what that work should look like. So remember to define the variable that you're using. X is the length of pregnancy in days. Since the distribution is approximately normal, we know that X is approximately normal with the mean 266 and the standard deviation of 16. Therefore, here's what my work starts out with. I'm trying to find the probability that X is bigger than 270. Convert it to a z-score. The z-score is 0.25. That yields a percentage of 0.4013. Remember, I forgot to mention in the first example that if you're using the table and you're looking up 0.5, that's going to give you something really close to 0.6, but since we're shading to the right here, that's why you subtract from 1. Just don't forget that that's a deal that's going on here if you're using the table versus a calculator. That means there's about a 40% chance a randomly selected woman's pregnancy is longer than 270 days. Please don't let it be me. Okay. Next question is number 2. Here is where we're doing, suppose we choose an SRS of 6 pregnant women. And so the mean of the sampling distribution, remember, is going to be the exact same as the mean of the original distribution, which is 266. Remember, the reason for that is because you got to remember what a sampling distribution is. The sampling distribution itself includes all possible samples of size 6. So those means are going to be exactly in the same place. Some of the samples will have an a larger mean. Some of the samples will have a smaller mean, but when you take every single possible sample of 6 pregnant women, the mean is going to be exactly the same as 266. So I'm going to write that out. So here's the right verbiage or lingo that you need to get down. Make sure you're paying close attention to these symbols here. The mean of all of the samples, the X bar, is the same as the mean of every single possible X. So the mu of X bar equals the mu of X, which is 266 days. The reason for that is because the sampling distribution includes all possible samples of size n. In this case, our n is 6. The vocab for that is that mu of X bar is an unbiased estimator. Remember, we talked about that and you read about that word unbiased. It's an unbiased estimator of mu of X. Compute the standard deviation. Make sure that before you do that math, your permission comes from checking that 10% condition. And it's obvious that there are more than 6 times 10, which is 60 pregnant women in the entire population. There's probably 60 pregnant women here in Palatine alone. So that's going to be okay. I'm going to write that out, and then I'm going to do my small sigma over radical n formula to find the new standard deviation, just like we did in the example above. Here's what all that looks like. So your condition check is making sure that you aren't sampling more than 10% of the population. So 6 times 10 is 60. There's for sure more than 60 pregnant women in the population. That means the 10% condition is checked. Yes, this is what you need to write in order to get full credit on the test or on an AP or anything like that regarding that 10% condition. Some people will just put 6 times 10 equals 60. And then I'm like, good story. You know how to multiply 6 times 10. Does that mean? What are you doing? Show exactly, make it clear exactly what you're checking for. So therefore, my sigma of x bar is sigma of x divided by radical n. 16 over radical 6 gives us that for our new sigma for the sampling distribution. And then I just put a note. Remember, whenever you take a sample, your variability decreases. So that's why our sigma went from 16 to the sigma of x bar, which is 6.532. So now I'm going to do the exact same thing I did up here pretty much, except I'm going to replace that 16 with my new standard deviation to answer question number 4. Here's what that work is going to look like. So remember, I did a little bit of defining and planning. I did check the 10% condition, but remember, I haven't checked the normal condition yet. So since, again, this distribution of length of pregnancies was approximately normal, that also defaults to mean our sampling distribution of x bar will also be normal. I did not need to use the CLT here. Remember, the CLT would only apply if n was bigger than or equal to 30, and in this case n is 6, so that wouldn't have worked in this case, but luckily we were told the sampling, or the original distribution is approximately normal, therefore the sampling distribution is also approximately normal. Here's what the work looks like. That's how I got my 0.2741. Remember, this is also a shading to the right section, so if you're using the table, you're subtracting from 1. And there's my interpretation. So let's go through this very last question here. This is a question about texting. So some of you are probably texting right now. Thanks for being rude while watching my video. Anyways, suppose that the number of texts sent during a typical day by a randomly selected high school student follows a, oh boy, right skewed distribution. This is interesting because we haven't done any problems that are right skewed yet, but that is going to be very important. So far, all the ones we were told they were approximately normal. Now it's right skewed, so I wonder what that means. Anyways, we've got a mean of 15 and a standard deviation of 35. Okay, so on average, you fools send 15 texts a day, but the standard deviation is very large. Okay, assuming that students in your school are typical texters, so like with this mean and this standard deviation, I guess, how likely is it that a random sample of 50 students will have sent more than a total of 1,000 texts in the last 24 hours? That is kind of a mouthful. Here's one thing I want you to be thinking about. We were not told our population distribution is approximately normal, so the next thing I'm thinking is, does that mean I could use the CLT? Heck yeah, we have a sample that's bigger than 30. In fact, our sample is 50. So that's going to take our normal condition check. So the other thing I need to do is the 10% condition check before I can start doing some math. Are there more than 50 times 10, 500 students, do you think, in this high school? And so it's a randomly selected high school. A lot of times it'll say a large high school or something like that. So it's okay in this case to assume that there are more than 500 students at this high school. Think about how many students are at Fremd. Close to 3,000, between 2,500 and 3,000. So definitely more than 500, okay, unless it was a pretty small high school. So we're going to go forward with both of those condition checks, and I'm also going to define X and write that out real quick. Here's all my defined stuff. So this is, again, like, keep in mind, free response questions, show all your work, show all your thinking, define the X that we're talking about here. X is the number of texts sent by a specific high school student, and then we're going to take a sample of those students. The sample is less than 10% of the population due to 10 times 50 being 500. You'll see in textbooks, and sometimes I write on keys and stuff, safe to assume there are more than 500 students at this school. Otherwise, it probably would have specified it's a really small high school, which why would they do that? Anyways, if it was this kind of an AP Stats question. So safe to assume there's more than 500 students at this school. Remember, show why that is useful information. That means that the 10% condition is checked. And in this case, the population distribution is not approximately normal. That's what this right skewed business is talking about. But thank goodness the CLT applies because n equals 50, which is greater than or equal to 30. So make sure you're showing all of that. Make sure that you've got that 30 in there as a comparison. So that means that the sampling distribution of X bar is approximately normal. This is important to have in your work as well. You'll lose a couple points if you don't specify what the CLT then tells you that you can do. Now finally it's time to find my new standard deviation and then go through the math and find the z-score and blah blah blah. Remember, you can't start changing your standard deviation until you have checked that 10% condition. So once that 10% condition checks out, your sigma of your X bars is the sigma X over radical N, which gives us 4.95. Now I'm ready to do my z-score calculation. Here's the weird thing though, is that I kind of am getting stuck when I'm writing my probability that X bar is greater than, do I use the 1,000? No, because that's the sample of 50 students, a total of 1,000. And I want to know, I guess, this X bar means mean. So if it's 50 students, total of 1,000 texts, how many does that mean they've each sent on average? 1,000 divided by 50 is 20. So 20 texts each on average. So make sure you're not using the 1,000. This is kind of a trick question, but that's where my 20 is going to come here. And so I'm going to convert that to a z-score. I'm going to take my 20 and I'm going to subtract it by the mean, which is 15, and divide by my, don't use the 35. Remember, we're using this 4.95 here. That's the standard deviation for the sampling distribution, so 4.95. That's going to give us a probability that z is greater than, what's the z-score here, 1.01. And that gives us a probability of 0.1562. And to finish it off, just so you can check, here is what my interpretation of that 15.62 actually means. That means there's about a 15.6% chance that a random sample of size 50, in this case, students have sent an average of 2,000 texts. You could also use the exact wording up here of 50 students who have sent more than a total of 1,000 texts, but I decided in my interpretation to use the 20 texts each, just because that explains a little bit better where that 20 came from. So just be careful here, read each question really carefully. Here's an example where our distribution is not starting to be originally normal, therefore the CLT applied here because of our sample size being large enough. Remember that large enough, which is a quote from the book, is defined as bigger than or equal to 30, which we have here in our condition check laid out nice and neat. And remember that was also in the last 24 hours. It's not like 20 texts each day or each week or anything like that. It's the last 24 hours due to the context of the question. All right, that's all, guys. Thanks for watching. Bring your questions to class tomorrow, okay? Have a good night.